Okay, welcome back. We're at 732 independent events of the multiplication rule. So we'll get started right away here. The good thing about today is this is just notes, so this video will be a little bit longer, but there's no homework after it. We're working through the whole worksheet. Okay, so number one, in Monopoly, if you roll doubles, you get to roll again. So what's the probability that Josh rolls a pair of dice and gets doubles in each of his first two rolls in the game of Monopoly? Realize this is not saying that he for sure gets doubles the first time. Okay, this is just saying his first two rolls. So we have two rolls. We're going to multiply those probabilities to figure out the probability of both of them. So doubles in if you're rolling two die, essentially means that you get a 1 and a 1, you get a 2 and a 2, a 3 and a 3, so on and so forth. So there's six numbers, so there's six possibilities of doubles, and you can look it up, but there are 36 possible ways to roll the dice because you can get a 1 and a 2, you can get a 2 and a 1. Those are different pairings of the dice, if the first or the second dice, and so on. So the first roll, his probability of getting a double is 6 out of 36. His second roll, it comes out the same. You roll the dice again, it's still a 6 out of 36. That simplifies to 1 out of 36 shot that both of his first two rolls are doubles. Okay, how about 3 times in a row? You get sent to jail if you do that in Monopoly. So 3 times in a row for his first three rolls, 6 out of 36 chance for the first roll, 6 out of 36 chance of doubles on the second roll, and a 6 out of 36 chance of doubles on the third roll. That simplifies to a 1 in 216 chance that you get doubles 3 times on your first three rolls. Okay. So question number two refers back to question 4 in the 731 notes and homework. So that was one of them that you guys did for homework. You discovered that when rolling a die, the event A of rolling an even number, okay, so your even number is going to come out to your 2, 4, and 6, okay, is your event A. Your B of rolling a multiple of 3, okay, so we're rolling a dice, we're talking about a multiple of 3 is just going to be the 3 and the 6. Okay, we're independent. We discovered that. Use the multiplication rule for independent events to show that the complements of these events are also independent. Okay, so we already know A. We know the probability of A was 3 out of 6 or 1/2. Okay, there's three things there. There's 6 total. Simplifies to 1/2, which means that the probability of A complement is also 1/2 because you can do 1 minus the probability of A to find the probability of A complement. That's your complement rule. Okay, the probability of B was 2 out of 6, which simplified to 1/3, which means that the probability of B, or the complement of B, is 2/3. Okay, and we found that the probability of A intersect B was 1/6, which means that the probability of A complement intersect B complement is 1/3, is the idea here. Okay, so where does that come from? Well, we know that A complement is the set of 1, 3, and 5. Okay, whatever's not in A. We know that B complement is the set of 1, 2, 4, and 5, whatever's not in B. And we know that A complement intersect B complement, so look at what these have in common, is the set of 1 and 5. Okay, so if I look at the probability of A complement times the probability of B complement, okay, this probability of A complement was 1/2 times the probability of B complement is 2/3. This is going to be equal to 2/6, okay, or 1/3. Okay, which, because there's two things in here out of 6, which simplifies to 1/3, is the same. So this and this are equal to each other, which means that these are independent events. Okay, using that idea, so we've verified that those two are independent. Okay. Now, usually I take a pause right here. I do a proof. Good news for you is we're on at-home learning. We're not going to do everything crazy. I did put it in here if you want to pause the video and look at it. It's kind of interesting to see how you can go through and you can prove this using all of the rules that we've gone through. And it's a good little review, but you do not have to. So feel free to skip over it. Okay, so we're moving on to number 3. In the US, people travel to work in many different ways. Table 1 represents a probability model for modes of transportation to work, which is based on data from a Bureau of Transportation survey. Okay, so these are the probabilities right here that they take these means of travel. Okay, what probability should replace a question mark in the probability model? Feel free to pause it if you want to figure it out on your own. but essentially all of these probabilities need to add up to 1, so we should put a 0.04 in here. Okay, what's the probability that a randomly selected worker walks or bikes to work or uses public transportation? So with this or right here, we're just putting these together, that they walk or bike to work, okay, is 0.03, or uses public transportation is a 0.05, and we're going to add those together, get 0.08. So an 8% chance that they bike or walk to work, okay? Realize there is no overlap of those, okay? And so that's why I don't have to subtract in this one, okay? What's the probability that a random selected worker does not drive him or herself to work? So when I see does not and there's only one thing listed, I'm going to do 1 minus my complement rule, okay? So driving himself to work is a 0.77. So I'm going to do 1 minus 0.77, and that's going to give me 0.23. Okay, 23% chance that they do not drive themselves to work. Okay, hopefully we got that idea down, but that's going to lead to more stuff. So number 4, assume that 2 U.S. workers, worker 1 and worker 2, are randomly selected. Okay, A, let event A be that worker 1 drives theirself to work. We're still using that chart from the first page. And let event B be that worker 2 drives themselves to work. Explain why events A and B are independent. Okay, and the idea here for the independent is just that A and B have nothing to do with each other. If you want to put it in a more vocab-based reason, they don't affect the outcome of each other. So one person driving themselves to work is not affecting the outcome of the other person driving themselves to work. Okay, so B looks at A intersect B. Okay, is the event that both workers drive themselves to work. Okay, so find, now we've decided that these are independent events, so we can use the rule of independence to solve this. Okay, so find the probability of A intersect B. Okay, so the probability of A intersect B is going to be from the probability of A times the probability of B, since we know that it's independent. Okay, so my probability of A is 0.77, the probability of the first person driving themselves to work is 0.77, times the probability of the second person is also 0.77, and that comes out to 0.5929, so about 59% chance that they're both driving themselves to work. Okay, what's the probability that neither of the drivers drives themselves to work? So we're saying the first person does not, 0.23, and we're saying the second person does not, 0.23. Okay, so again, 1 minus the 0.77 gave us the 0.23, that they're not driving themselves to work. This comes out to a 0.0529, so about a 5% chance that neither of them are driving themselves to work. Now, this is where it gets tricky. What's the probability that exactly one of the workers drives themselves to work? Okay, so some people get a little bit confused here in how to do this, okay? But what we have to realize is either the first one could possibly drive themselves to work and the second one could not, okay? So we have the fact that A decides to drive themselves to work and B doesn't, but we also have the fact that B decides not to drive to work and A decides to drive to work. Okay, we have to add these two probabilities together, okay, which both of these come out to 0.1771, so essentially I can just do that times 2, and it's going to come out to 0.3542. So it's a 35% chance that exactly one of the workers drives themselves to work, okay. So our last one here, human blood, comes in different types. Each person has a specific A, B, or O type. So this is real information here. Learn a little bit of science as you're doing your math. So you can have A, B, AB, or O type blood. And you have an Rh factor, either positive or negative. Okay. So hence, if you are O positive, your ABO type is O, and your Rh factor is positive. Okay. Blood types are not evenly distributed. Table 2 shows the probability distribution of different blood types in the US. Okay, so this is saying that this is an A positive would be 35% chance, and so on and so forth from there. Okay, so blood types become very important when a blood transfusion is needed. Patients must receive a blood type that is compatible with their own, or they might die. Any patient with Rh positive blood, so any of the positives, can safely receive a transfusion of type O positive blood. what is the probability that a randomly selected person could receive a transfusion of type O positive blood? So what we want to do is we want to find all of these people, okay? And these are already probabilities, so I can just put them together. I'm doing the 0.357 plus the 0.085 plus 0.034 plus 0.374. And if you add all of those together, you get 0.85, or you get an 85% chance that that person can receive O positive blood. Okay, so two people are selected at random. What's the probability that both could receive a transfusion of type O positive blood? Okay, so the first person receiving a transfusion of O positive blood, or that could receive it, would be a 0.85% chance. That's why we just found this. Okay, times the second person has that same chance of being able to receive it. Okay, so that comes out to 0.7225. Okay, 72% chance that both of them can receive that. Now, put this in perspective. Some of you might be like, oh, 85% chance, that's pretty good. But the 15% that cannot receive that are not going to be very happy. And now that we have two people involved, that goes down even further. Okay, what's the probability that neither of them could receive a transfusion of O positive blood? So we're saying neither of them can receive it. That's a 0.15 first, okay? And that the second person can't receive it. That's also a 0.15. Okay, that comes out to 0.0225. So there's only a 2% chance that neither of them can receive it. That's not too bad, but I'm pretty sure that those 2% would not be very happy if you just gave everybody O positive blood. Okay, and so lastly, what's the probability that at least one of them could receive a transfusion? So our last one talked about exactly one. This is a different. This is at least one of them. So what we have to realize is that person one could possibly receive it. Okay, that would be a 0.85, and person two could possibly receive it. So both of them receive it. That's at least one. Okay, we could, then we're going to add that to my next possibility is that person one could not receive it, and person two could. So we have one person that's at least one of them could receive that. And then we also have it that person one could receive it, but person two could not. So that's at least one. The only thing we're missing here is that both of them could not receive it. Okay, so I can add all of those together when I multiply them, and it comes out to 0.9775, or about a 98% chance that at least one of them could receive the O positive blood. You can also find this, like I just said, the only example that is not used here for at least one is that neither of them can receive it. So I can do the 1 minus the 0.0225. Those will come out the same. But you do have a 98% chance that at least one of them could receive that O positive blood transfusion. Okay, let that sink in. Feel free to look up some other ideas, but just hang in there for today and go on with some other homework. Hope you guys are doing well.